Can we?
Yeah, sure.
And it's a pleasure to introduce Tomasz Lipniacki from Warsaw, the Academy of Sciences in Warsaw, and he will be one of the few people who can pronounce the names of his collaborators properly.
What about you?
The writing is on the wall, so we may start.
Okay. Thank you very much for having me here and giving opportunity to present this work. So as Konrad mentioned, this is the work done by PhD student Marek Kochańczyk. Paweł Wuk is not my PhD student now. He is Piotrek Szymczak PhD student, but he was working with me as a master degree student, and Jan Jaruszewicz. So Marek Kochańczyk wrote a very nice software, we call it Spatkin, which enables this stochastic, specially extended simulation. The work is based on these simulations. So he contributed mostly to this work. So all the talk is about bistability and stochasticity. So it is the motivation is biological. People used to think that bistability in cell regulation is needed for taking cell fate decisions. So if cell is to stimulate and is to go, let's say, to the cell cycle arrest or apoptosis controlled death or proliferation, this is due to the bistability in the system. So it has some time to switch between these possible paths, but after that it gets stuck in one path and perform the well-defined program of doing something. Like we are switching close to the coffee tea machine, but finally we are trying to perform one of these programs possible. So, and of course, some decisions are like irreversible. It can go to cell cycle arrest, but after the conditions change, it can resume and go back to the cell cycle. So there should be possibility to switch between these steady states. So there are like at least 3 ways how this switching can be accomplished. So if we have a small, perfectly mixed system, it can be due to the stochastic transition. The number of reacting molecules is small, so there is a huge stochastic noise, and it can switch from one steady state to the other with some transition rates which are decreasing exponentially with number of reacting molecules. It can be due to heteroclinic traveling waves if we have specially extended system and we do something in one place and excite it to the more stable steady state, then the traveling wave can propagate and all the system can be converted to that most stable steady state. Or it may happen that these heteroclinic traveling waves can be induced locally by noise. So basically most of the talk is about these stochastically induced traveling waves, which are induced stochastically, but as you will see, they propagate mostly in a deterministic fashion. So people are using like 4 approaches to simulate cell dynamics. The simplest approach is to do ODEs. We are assuming that cell is small, it is perfectly mixed, and the number of molecules is large, so you can do ODEs. For sure, this is not true. If you mix the cell, it will be no longer alive, so cell is not mixed. And the number of molecules is also small. Basically, we have like 2 gene copies per each gene, so this is the lowest number, and the fact that we have only 2 gene copies introduces huge noise. So if we have if we have small diffusion but a large number of molecules, we can do PDEs. This is more reasonable approach. If the process is slow enough that we consider cell perfectly mixed, in some cases we can do such things. If the process is slow with respect to if the chemical reactions are slow with respect to the diffusion, we can say that it's perfectly mixed, and we can perform the stochastic simulation without spatial resolution. But in most cases, seems, and I will argue about that, we have to do the spatially extended kinetic Monte Carlo. So we have to take care about spatial resolution. And okay, so here are the estimation why this can be important. So okay, if we take diffusion and reaction rate, so reaction rate is 1 per second. This is the typical reaction rate, and the diffusion coefficient, we can get the dimension square. So if d square, if the dimension square is much smaller than diffusion over k, we can say that this compartment is perfectly mixed. This means that a given molecule will completely forget its position between two subsequent reactions. Okay, if these two, if d square equal s is comparable with diffusion over k, we can say that the compartment is communicated. So if one molecule changes its state because of reaction in one place of the compartment, it has a good chance to reach the other place of the compartment without changing this state. So we can introduce such terminology. Okay, so now we can look what are the real numbers in the cell. So the diffusion on cell membrane, it is of order of 0.01 to 0.1 micrometer square per second. The reaction rate is 1 per second. So it implies that the area of communicated region is much less than micrometer square. And the cell diameter, eukaryotic, our cells are like 10 micrometers of diameter. So the area of communicated region is much smaller than the area of the cell membrane, and the number of cells at this surface and the number of molecules on this surface fragment is very small. It will be like tens or small hundreds. So because these are the molecules which instantaneously know about each other, you can expect that the magnitude of stochasticity in this regulation will be huge, even if the total number of molecules on the membrane is high. Yeah? Because these molecules, they don't know about each other at a given time point. They can communicate by means of traveling waves, but at a given time point, they don't know about each other. Okay, so to study these effects, this is like a long-going program. We wrote, Marek Kochanczyk, in fact, wrote the software enabling these kinetic Monte Carlo simulations on the membrane. So here I want to present the simplest model, the simplest realistic model with bistability, and show you the results. So the rules are following. We will consider kinase. This is basically the type of protein which is responsible of transmitting signals in the cell. And this kinase can be in three states. It can be unphosphorylated. It can be phosphorylated at one residue, or it can be phosphorylated at both its residues. Typically, the story is that when kinase is not phosphorylated, it has a very low enzymatic activity, and when it is phosphorylated, it has a very high enzymatic activity. So the difference in enzymatic activity between this state and this state, it can be like 10,000-fold. This is a typical difference, or 1,000-fold. And when it has phosphorylated at one place, it has the activity somewhere between. Okay, and the second considered molecule will be the phosphatase. The phosphatase is the enzyme which may take the phosphor group out of the kinase or any other protein, if it is specific to this. So we will assume that that kinase may phosphorylate the neighboring kinase. This is called transphosphorylation. So if they are in contact, so for example, this kinase may phosphorylate this kinase to the double phosphorylated state, or it may phosphorylate this kinase to the singly phosphorylated state, and then to doubly phosphorylated state. And this phosphatase may dephosphorylate this kinase to unphosphorylated state like this, right? So if these molecules are in contact, these reactions may happen. And in addition, we assume that these molecules diffuse, so their motion, they can go to the neighboring site if this site is empty.
Sorry, what did you say the dark brown represented?
Dark brown represent double phosphorylated kinase. So this is the kinase which has phosphorylated to its residues, and this kind.
I was just puzzled. It was a different shade, but okay.
Okay, sorry. Yeah, and this kinase has the highest catalytic activity. So it will phosphorylate the neighboring kinases with the highest efficiency, with the highest rate. Okay? I mean, are these rules clear? This will be the end of the biology, but...
Do you have those equations listed?
Yes, I will have the reactions listed in a
But is it meant to be in 2 dimensions or in 3?
This is in 2 dimensions, so it all takes place on the membrane. Okay, so all simulations are in 2 dimensions. I think that the importance of these considerations is mostly on the membrane where diffusion is the slowest. The diffusion on membrane is basically order of magnitude slower than in the cytosol.
So when you would do the same kind of estimate with S and
yeah.
squared in the cell, it would be well mixed? Or?
No, it will not be well mixed. It will be not well mixed, but the area of but the volume of the communicated region will be a bigger fraction of cell volume. Okay, so right, and the rules are here. Okay, so when 2 kinases meet, one kinase can phosphorylate the other kinase, okay? And this is accomplished with rate 2 times C1. When phosphorylated kinase meet unphosphorylated kinase, it can phosphorylate it with rate 2 times C2. When double phosphorylated kinase meets unphosphorylated kinase, it can phosphorylate it with the rate 2 times C3, and here it is when phosphorylated kinase meet unphosphorylated. Okay, this unphosphorylated kinase phosphorylated further to the state, to the double phosphorylated state. This single phosphorylated kinase phosphorylate this kinase to double phosphorylated state, and so on. So the 2 appears here because here there are 2 possibilities. So this kinase can be phosphorylated in two places, in place 1 and in place 2. So there is like twice higher chance that we transit from K to Kp than from Kp to Kpp. Because if you transit from Kp to Kpp, there is only one place left for phosphorylation.
But I don't understand this. The second equation on the left-hand side,
Right.
same as the left-hand side of the top equation on the right. So does that mean that there are two possibilities for K, for the product of the reaction of K with Kp?
Sorry, say again.
I mean, the second equation,
The second here,
yeah, it's K plus Kp.
right,
And there at the top, on the right-hand side now,
right,
no, at the top on the right-hand side.
They don't commute.
top on the
No,
right.
Commute.
Yeah,
Yeah, they don't commute.
interesting.
Okay.
There are two outcomes for that reaction, two possible.
Is it obvious that there should be C1 in the left row and in the left column and
Yeah.
the right one?
It's
Then-
not-
Yeah,
It's not
yeah, it is obvious because the enzyme here is K, right? In both cases, maybe I should write the enzyme first. But the enzyme here is K, so K phosphorylate this K, so this K becomes Kp, and here this enzyme K phosphorylate this Kp to become Kpp.
So the order matters,
Yeah,
the way you've written.
yeah. So what is needed to remember is that this considered as an enzyme phosphorylate with rate C1. This considered as an enzyme phosphorylate with rate C2 larger than C1, and this phosphorylate with rate C3 larger than C2 and C1. So, okay, and there are dephosphorylation reactions. So when phosphatase meet with phosphorylated kinase, it can dephosphorylate it. And again, here the rate is multiplied by 2 because there are two places which can be dephosphorylated. Okay, so and we will consider the following. So D0 is set 1. This just measure the time scale. So we have the freedom to set one parameter equal 1. C2 is the smallest phosphorylation rate. C1 is the smallest phosphorylation rate by the kinase of very low activity. C2 will consider 3 values. Just for this talk, we'll consider 3 values of C2, and C4 and C3 is equal 4. This assures that the system is bistable, if provided that C1 and C2 are small. Okay, I mean C3 must be basically 4 times approximately 4 times D0 to make the system bistable for small values. At least that value to make it bistable. Okay, so and all simulations are performed using the Gillespie algorithm. So for those who are not familiar with this, it works like this. You have to sum all the reaction propensities. Propensity, this is a probability divided by dt. So this is the probability in a infinitesimally small time interval. Okay, so you have to find all reactions, including movements and so on, calculate this total propensity, draw the time to first reaction, yeah, when P is the random number, and then if you know the time of first reaction, you draw which reaction take place having the particular propensities of any of these reactions. You perform this reaction, so you update reaction list and repeat it again. So at each step you perform the single reaction. It can be like phosphorylation or dephosphorylation or movement of a particular
So you really want the draw time to be negative.
no, you may not draw.
It must be negative.
Okay, so sorry, there is minus here. Sorry.
Thank you.
So-
So what's the spatial update rule? I mean, what's the reaction rule for the spatial updates for moving space?
So there is a propensity of moving to the neighboring empty cell. Okay.
There's some random walk? I mean,
Yeah, this is like random walk. So each molecules have the same propensity that it will move to the neighboring empty place.
But if it's random walk, if there are no other
Yeah, random walk with
reactions,
obstacles.
if there are, then
Yeah, it has-
will also stay in the same place.
Yeah, but morphon is like independent to the reaction. So or the reaction takes place or the motion takes place, and this is in the same list. Sorry, there is minus here. This is like well established 30 years ago, the simulation algorithm. Okay, and if we want to compare the perfectly mixed system in which all these molecules can react one with each other. This is typically what you are doing writing mass law equations. You are assumed that every molecule in the reaction chamber can react with every molecule. Yeah? So we want to have this limit of infinite diffusion. This is the limit of infinite diffusion, and we want to compare it with kinetic Monte Carlo simulations doing very large diffusion. So we have to rescale coefficients. So we do it in a following way. So we assume that a given reaction rate in a Gillespie here means the perfectly mixed is the 6 times rho, the density of the enzyme, times the reaction rate in kinetic Monte Carlo. So this comes from the fact that, okay, in kinetic Monte Carlo, the reaction takes only place if two molecules are in contact. So if we have to, so 6 times rho, it is the expected value of neighbors of the enzyme, yeah? Because each molecule has 6 neighbors, so rho, the fraction of fillet membrane, gives us the expected number of neighbors. So this is the easy way to convert it, and it works. So when we perform this perfectly mixed simulations which correspond to infinite diffusion, and we perform the simulations on the small domain 20 by 20 with very high mobility equal 10,000. So the typical reaction rate was like 1, the phosphorylation, and we take that the morphon is 10 times more probable than reaction. Yeah? So this is like limit of very high diffusion. We are getting basically the same bimodal distribution. This is we are checking it for bimodal distributions because they are very sensitive for parameters. So a small change of parameters makes that this hump becomes even bigger and this even smaller.
Talking about parameters, can I go back to the previous page? Because what is the parameter rho? Because the on the previous page. Yeah, because these units don't agree if rho is 1 over volume. What do you mean by density?
I mean rho, it is the fraction of cell membrane taken by enzyme. So rho is like 1/2 or 1/3.
So it's not really density.
Yeah. So this is the so 6 rho.
Probability to occupy.
Yeah, probability to occupy, and 6 rho, it is the expected number of enzyme molecules which which are in the immediate vicinity of a given molecule, right? Rho is the fractional density of enzymes, and each enzyme has 6 neighbors, so 6 rho is the expected number of enzymes in the immediate vicinity of any given molecule.
Why 6? Why a hexagon lattice?
Because why we are using hexagonal lattice? Because in hexagonal lattice, all your neighbors are equal. In rectangular lattice, you have these neighbors on diagonal, and you don't really know how to treat them. So people doing this, the flat simulations, they basically prefer hexagonal lattice because all neighbors are equal. Okay, and again, we can verify it. We can run these perfectly mixed simulations, which are going very fast, and kinetic Monte Carlo simulation with these transformed parameters and these trajectories. So this is the fraction of singly and double phosphorylated kinases. So we sum here Kp plus Kpp, or subtract K from 1. Yeah, it's switch in a similar way, and the distribution is similar. Okay, so this was the introduction. Sorry that it took so much time, and now I'm going to the results. So first we can look what happens if we change the mobility of all the molecules and we change the size of the domain. So we keep all the reactions rate constant and change just the mobility, how they move, or change the reaction rate, and looked into the steady state probability distribution. So let's fix on this.
What's on the horizontal axis?
On horizon here, right? Okay, so here is the fraction of singly and doubly phosphorylated kinase. So activated kinase. So this fraction can be at most 1 if all kinases are phosphorylated or doubly phosphorylated, or 0 if they are all unphosphorylated. Okay, and this is the steady state probability distribution. So this state here corresponds basically to active state. Most of the kinases are active. Yeah, the very relative fraction is close to 1, and this corresponds to inactive state. Okay, so when we go this row, changing the mobility or motility, biologists prefer motility. So when we change the mobility of these kinases, we see that the systems became inactive. So all reactions rules are kept constant. We just changed the diffusion and learned that the system became inactive. Okay, so this is something tricky. Or you can take this column and change the volume of the system. So here the system is active, and when we do the larger volume, here the system is inactive, and when we take the larger volume, the system became active. Right.
So what about the initial condition you put in some?
It doesn't matter. This is an extremely long-rank simulation, or rather composition of many extremely long-rank simulations, like 1,000 processors for 3 months.
Yes, but you had those guys that can dephosphorylate.
Right.
Yes, and the fraction is kept constant of these guys as the volume is increased or decreased. Or?
Yeah, right. So everything. I mean,
So everything is uniform. You just
yeah. I just rescaled I just changed the size of the reactor. So I changed the number of molecules.
Yes, but
keeping
proportionally to the.
Yeah, right. Okay, but
Everything gets excited when they cannot communicate well, essentially.
no.
Small diffusion.
No. Okay. But this I think is I mean, this effect I think is interesting, that changing the motility makes that the system. Here you see you change the motility and the system inactivates. So they can communicate and then became inactive. Here you change the size of the compartment and the system became active. So your theory is not as good. Okay, but this is interesting, but I think that I have something which was more puzzling to us, and I mean at some stage. So let's focus on this. So what we see here, we take the large motility 3000 and we take the volume 30 by 30. I take the closer eye on it, so the system is in active state, right? This is the same picture for infinite motility or higher motility. Infinite means that we do the perfectly mixed compartment. So basically, when we have a large motility, very large motility, and volume 30 by 30, the system is inactive. So, and now what we do, we take the size of the compartment 30 by 1000, okay, by 1100, and start that this part is active. So here the molecules are active. So what we see is that the activatory traveling wave propagates. So when we take the small compartment 30 by 30, right, it wants to be in an inactive state. But when we take a larger compartment and make a part of it active, the activatory traveling wave propagates and all compartments became active.
And if you would not make a part of it active, but just wait for a very long time, would
Right.
the large compartment
Right.
go
Right.
spontaneously?
I am going to this. I am going to this. So let's focus here. We take 20 by 20, and okay. So again, this likes to be inactive, but there is a tiny probability here that it is active. This probability is from these transition times. You can calculate the probability exactly. So this is like 6%. And when we wait enough long, it spontaneously activates in that place. We take the volume 20 by 1000. It's the fraction, only fraction of that volume. So it spontaneously activates, and the traveling waves will propagate. Yeah. So looks that when we
Does it always do it in the middle?
No, it do it in a arbitrary place. So looks that when we have, okay, these compartments can be considered as perfectly mixed for that diffusion. And this longer compartment is not perfectly mixed, right? So one is like a regime of perfectly mixed compartment, and the other is regime, rather deterministic regime in a sense, after it's switched on, of traveling waves propagation. And there are different rules. So I want to come to do, and I started that way, we started opposite way. So we first do that math, and then we do the simulations, but I prefer to present it like this. So we can define stochastic attractor. So we take the perfectly mixed system and define that stochastic attractor. We have two stable steady states deterministically, and we define the global stochastic attractor as the state in which the probability density distribution concentrates in the limit of n going to the infinity. And we may define deterministic attractor. We do the PDEs, and we define deterministic attractor as the most stable steady state from which the traveling waves propagate. So this state width, right? And these two attractors can be different, okay? And we do it considering a very simple birth and death process. Birth and death process is the process in which we can add one molecule or subtract one molecule or from a given pool. So we have the birth rate and death rate, this defines W, and W, because this is one-dimensional, it has its own potential. So this will be called the deterministic potential. And now we can consider the stochastic process, again with this birth and death rates, but they are like by one and subtracting one. So this deterministic potential defines the sign of the traveling waves in one-dimensional case. Okay, and let's look closer to this. So if we have this birth and death process, we can write this equilibrium equation. It comes from the fact that when we look into steady state, the transitions from left to right must equal to the amount of transitions from right to left. So we are like hoping like this, and this is this equation. So this can be solved like this. So we can solve it completely. We can pass to the, okay, we can take log of this and pass to the very large U limit. So U is like volume, but it's not a real volume because it is perfectly mixed. So U like scales the number of molecules, and we can find the steady state probability distribution. Okay, and here it is like potential, right? But this potential, it is not B minus D, but this is log B over D. Okay, so you clearly see that this potential is different than this potential, right? And if we so we have the deterministic potential and stochastic potential. So the global minimum of deterministic potential defines the most stable steady state when we look into traveling waves, and the global minimum of stochastic potential defines the steady state in which probability density function concentrates in the limit of high number of molecules, but perfectly mixed, right? So now we can...
Going back to your simulations, what would be the example when
okay.
you give this?
Okay, so the minimum of stochastic potential gives us the state in which we have relatively small volume, like 30 by 30, and large diffusion. Okay? And deterministic potential describes these traveling waves, which are almost deterministic because there is a large diffusion. So
they become important for different volume of the system.
Right.
Not for the same volume.
Right. Right. For a different volume of the system. Okay, so you can understand this a following way. So you can add some constant term to birth and death and say that this is a flow of active kinase to and from the compartment. So this is something which increases the birth and death. So you can think that you have a compartment and F is flowing in and F is flowing out. So this is like we have this long volume of thickness 30 and length 1000, and we just take 30 by 30 and say that something is going in, something is going out, right? Okay. So if we do this, we obtain this modified birth and death rates, and you can first, for F going to the infinity, the stochastic potential converges to the deterministic potential divided by 1 over F. Yeah, this can be easily seen if you add F here, and F will be going to the infinity, will go to this potential. So if there will be a large diffusion between these two subcompartments, then we will go to the deterministic limit, and this is also checked here. So what we are showing here, it is let's say for f equals 0, so there is just no flow. So delta 3 means that that if parameters x1 and x2 are in the subdomain delta 3, then the steady state probability distribution concentrates in active state delta x3, and if we are here, then this steady state distribution concentrates in inactive state delta 1. So this is the separatrix for no flow, and this is the separatrix for infinite flow. And this separatrix for infinite flow, this is exactly the separatrix we are getting in the classical potential. Yeah. So this is the explanation why we, and this is how we reach it, studying this simpler system which we can take analytically, why when we have connected compartments like 30 by 30 compartment, which likes to be inactive because it is inactive because it is perfectly mixed, so the stochastic potentials apply. And when we pack these compartments together, so the signal can transfer from one compartment to the other compartment, the traveling wave propagates, so they all became active, and they will remain active forever, because if they spontaneously inactivate somewhere, the traveling waves will immediately seal the gap. So, okay. And here we have the similar situation. This can be done only numerically. So here are our coefficients C1 and C2. C3 is 4 and D0 is 1 for that plot. So this is the condition for deterministic standing wave. Okay, so if C1 and C2 are on that line, then, and we do the partial differential equations, we will get the deterministic standing, the standing traveling wave. Okay, this is the line for which we get the stochastic bimodality in the limit of n going to the infinity. So none of these states will win. Yeah. So above this state, the system, the perfect. Okay. So above this line, the perfectly mixed system is active. Below this line, the perfectly mixed system is inactive, and below this line, the deterministic traveling waves propagate, so the system became inactive, and here it propagates that the system became active. So here there is plenty of room to make that the deterministic traveling waves propagate and the system is activates the system, while if we take the perfectly mixed compartment, it became inactive. So having the long domain, we reach the limit of deterministic traveling waves propagation, which can be switched stochastically. Yeah. But then it will propagate in a deterministic way. So we can check whether we are reaching this limit calculating the traveling wave velocity. So having the fraction of the activated kinase in the compartment, we can calculate, we can do the plenty of simulations and calculate this velocity. So as you remember, the velocity of traveling wave scales as a square root of the diffusion. So this is for PDEs, and this is for our kinetic Monte Carlo simulation. So really, in the limit of large diffusion, we must have a large diffusion, because to reach the deterministic limit, we must have a lot of molecules on the length scale, yeah, wavelength scale, yeah. So we only hope to reach this limit perfectly in the case of large diffusion. So we are getting this limit.
It's a nonlinear wave when you're in the PDE.
Non-linear in what sense? I mean, This is like heteroclinic, so it links to stable steady states, right? So it is heteroclinic traveling wave. But
Well, I know what I mean by nonlinear, but in the context of partial differential equations.
It's not a linear PD, it's a nonlinear PD.
yeah, right. It must be nonlinear to get by stability, right?
But it looks like something evaluated at x plus ct, or not?
Right.
It does look like that.
Right. I mean, there is a fixed profile which is moving. It is a little bit non-monotonous profile, but a little
Fixed
bit.
profile, that's,
Yeah,
I think.
but it is a fixed profile moving it exactly. So, okay. And then we can look into these excitations having the more realistic compartment, not long and thin. So we can see that it can excite in a given place, and then it will propagate as a traveling wave. So this behavior is clearly seen here. So if you run a bunch of this simulation, you see that there is nothing. When it flips, this is the traveling wave propagation. So here is, again, the total fraction of active kinase. So this is the traveling wave propagation when it steps. So it is like, if you are interested how long it takes to activate that state, what really is meaningful is this waiting time, right? Because this wave propagation time is rather very short, and this time can be long, and it is natural question how long can be that time, what governs this time. So if we have perfectly mixed system, as I said, this switch off and on time is proportional to the exponent of number of molecules, because it measures the magnitude of noise. So in specially extended system, the dependence is much different. When we take the volume of the reactor, it first grows with the volume of the reactor, with two coefficients, because we more molecules have to flip together. Yeah, because if initially when we are increasing the volume of the reactor, we are still in the limit that all reactor is well mixed. Yeah. So initially it should grow like exponentially, because even increasing the reactor, we are still in the limit that it is well mixed. Yeah, there is a log scale here. Yeah, so. But then the reactor is much larger than the well-mixed reactor, and it decreases linearly because there are more and more places in reactor where this flip can take place, right? And it is enough that it flip in one place, and then this traveling wave will propagate. So this dependence on the size of the reactor is completely different from perfectly mixed reactor. Basically, in this interesting regime, the waiting time to flip on decreases linearly with the size of the reactor, while in perfectly mixed case, it increases exponentially with number of molecules. So the behavior is like completely different. And then there is a question how it scales with the diffusion. So this is for the 200 by 200. So it scales exponentially with the diffusion. Why it is so? Because to start the traveling wave propagation, we have to switch on the size which is proportional to the diffusion divided by the reaction rate. Right? So to the area which must become on, yeah, diameter of this area is like over reaction rate. Yeah, so the So the number of molecules in this area is density times S. So this expected waiting time will be proportional to the exponent of the diffusion. When we take this longer volume, it should be proportional to the square root of the diffusion, because one dimension is fixed. So this starting region is like a thin rectangular, but this square root dependence is by far not perfect. So there are some other effects which shows up. Okay, so I am at the conclusion. So first, and I skip a big part of it, diffusion size and shape of the domain control the steady state probabilities and transition rates between these two steady states in spatially extended system. There are many ways how diffusion controls this steady state. So this traveling wave propagation is by far not one way. We identify several different mechanisms of this control. But I mostly concentrate on the fact that rates of steady state to state transitions, they decrease linearly with the system size, which is completely different to the perfectly mixed systems, and increase exponentially with the diffusion. So the message to take home is that if you have the spatially distributed system, the stochasticity of that system is not determined by the number of molecules. There may be a huge number of molecules, but it still can switch on or off depending on what is on or off if the diffusion is sufficiently small. So this switching on mechanism is like switch on locally, then distribute it as a traveling wave. Okay, I'm done.
Yes, questions?
Perhaps I missed it in the beginning. Is there a simple reason why there are no tri-stability despite 3 degrees of phosphorylation?
Why there is
No tri-stability. You have 0 phosphorylation, 1 and 2, and yet you grouped 1 and 2 together.
Yeah, there is
No 3 stable chemically.
no. If you write ODEs for that system, it will be the third order ODE. So there are basically 2 steady states. One steady state is that most of the kinase is in unphosphorylated state. So it is like 90% dependent on parameters. And the other state is the state when basically half of kinase is in singly phosphorylated state and 30% or 40% of kinase is in double phosphorylated state.
So you say there couldn't be a case where it's only double,
No.
only single.
No. I mean, the system is too simple. You are just getting third order equation, so it has 3 steady states. One is unstable, and the other 2 are stable. Yeah, so the system is too simple to have 3. Triability, how it is? Bistability?
Tri-stability.
Tri-stability.
Yeah, a question. Could you also get some non-trivial patterns in the space, like in Turing system, where you have some points where the system is active and some other points where it's not non-active or
Not in this setup. I mean, in Turing systems, we have 2 different diffusion coefficients.
yes, you have inhibitor and
And
activator.
here we assume that the diffusion coefficient for all components is the same. But I mean, for sure there should be a limit in which in kinetic Monte Carlo simulations you will get the Turing pattern. It depends on the relative diffusion coefficients, but also basically to reach the deterministic limit, the diffusion coefficient must be high enough to have a large number of molecules on the traveling wavelength scale, right? This is the, if we have the gas, so this is when we are reaching the continuous limit. On the wavelength scale, we must have a large number of molecules.
What do you mean by traveling wavelengths?
Okay, you have like
Propagating front. There is no
so,
wavelength.
no, that is exactly. I mean, all waves have their length. Okay, so the length scale, it is that distance, right? So this is
So it's the width of the front, not the length scale, not the wavelength.
this is traveling wave. Okay, let's say that this is the width of the front.
The length of the wave.
Okay, right. So
So it's neither wave nor wavelength.
it is traveling wave. Okay, everybody is calling this traveling wave.
Yeah, it's like a shock wave.
It's like a shock
The
wave.
main wall width.
Okay. So this is, I don't know if I said this, this is the result of the PDE simulation, which is very easy. Yeah, so you can see that it's a little bit non-monotonous.
Can you determine that shape analytically from the PDE? You assume it's a function of, well, call it x minus ct.
X minus VT is.
You get an ordinary differential equation.
I get the ordinary different. No, I think I cannot solve it still.
It's a nasty nonlinearity.
Yeah,
Yeah.
but
But it's autonomous.
Oh yeah.
But I didn't try hard, you know. I didn't try hard, so maybe it is possible. But this is the numerical. I mean, the numerics here is so
I think
simple.
it'd be worth trying hard on that one.
Yeah, I mean, having the analytical. Yeah, right.
So Tomasz is averse to analytical finesse. I know that.
No, you know,
Just like
I just would like to check if this traveling wave, yeah, here we plot the concentration of inactive singly and doubly phosphorylated kinase, right? So this is coming from, this corresponds to that state.
Yeah.
To that state, we were interested whether this transition phenomena is.
So it gets the width of the front increases with time. Becomes more.
No, the width.
It's
This
sharper.
is like traveling wave, so the width of the front stays constant. Just this front moves, right? All this
But if you-
moves.
But if you
This is like here, yeah. This front, okay. This is far here because this is far here because we just start from this condition. It gets immediately smoothed and then moves like this. So we start from the
yes.
front like this, but it immediately smooths, and this length is proportional to the square root of the diffusion. So if you have large diffusion, then the number of molecules on that length will be large. So the PDE limit of this kinetic Monte Carlo will work well. If you have a small diffusion, then there will be few molecules, so this PDE limit will not work well. Yeah, here it is like the length is like 100, so here we have 30 by 100, so the number of molecules is like hundreds.
And what determines the speed of propagation of this wave?
This is again square root of the diffusion. I think I show it. Okay. So here is the diffusion.
Length times the
So
duration.
so it is. So the velocity. So the velocity. Oh, okay. So the velocity is
This
the.
times k.
Is the right. Right. This is
You
the
need to multiply it by k.
by k.
Multiply it, yeah.
Yeah. Right. By k. Okay, so this is the velocity, and this is this length L is diff over K.
With it.
Yes, exactly. Right.
But I understand that your simulations were in the situation and the number of particles was constant, right?
Right.
But in a cell, even if it is a membrane or something, that this number would not be constant, right? But perhaps more proper simulations would be in the grand canonical ensemble, when these phosphorylases are, the concentration of them is controlled on average, and so on. How would this affect the results?
Okay, so people measured. There are very few. It is difficult, but people observe these phosphorylation waves on the membrane, and the velocity. There is a Sark family kinase, very important for immune cells, and they observe the phosphorylation wave of heteroclinic phosphorylation wave of a Sark, and the velocity was 17 nanometers per second. So it means that it takes to go from pole to pole of the cell in about 10 minutes. So in a 10-minute scale, I think we can assume that
No, but you're talking about the time for the wave to propagate, right? When talking
Right.
about the supply of the particles,
Yeah, okay.
the fixed
Yeah, so
number of particle situations.
yeah, right. So if you are waiting for the switch on or switch off, of course, this local conditions and local density of course, here you may have also increase in the local density by fluctuations, but in a cell you may get this local increase by transport to the membrane or by some lipid troughs on the membrane and so on. So, for example, you can induce these traveling waves when you locally decrease the diffusion coefficient. So in reality, yeah, this behavior, or you can induce these traveling waves by transporting locally kinases from the cytosol to the membrane. So you make the higher concentration, so you can start there and then propagate. Here is the example that the diffusion here is as large as 1,000, so this wave may not spontaneously be initiated because, as I told you, this waiting times increases exponentially with the diffusion. So if I increase diffusion threefold, this waiting time will be very, very long, longer than life of the cell. But I can activate this traveling waves by making the diffusion locally here smaller. So it will activate here and then propagate. So,
Any questions from non-Polish community?
That's a
Roman?
Are your traveling waves solitonic in nature or not?
no.
So did you try to collide two waves? You don't have those simulations?
No, I mean, solitonic waves may not be heteroclinic, I think. They must be homoclinic, right? That you start from
By solitonic, what I mean is if you, first of all, it keeps the shape as it propagates. Second,
yeah, they can go,
colliding could go through each other.
yeah.
It doesn't happen here.
You didn't try, you have
Well,
to start.
No,
But I don't
but
uniform.
they cannot, I mean, there is a dissipation here. I have the potential, right? So all these, in a deterministic limit, they propagate from most stable to the less stable steady state, yeah?
They don't have a trailing edge.
Yeah, so
It's the red that
so you can, yeah, so, okay, so you can take a potential, I mean, in one dimension. In two-dimensional case, it is not so, but in one-dimensional case, when I have, when kinase can be only in two states, yeah, this has, let's say, lower potential than this, so this may propagate that way. So it cannot propagate in opposite way. Yeah?
So there's
Because
no way
there
of
is
spontaneously
Yeah, but you
going
can start in
backwards.
2 places and see what will happen.
no, but they cannot propagate in 2 directions. You see, there is a dissipation here. So it can propagate if that state, if state S1 has a lower potential than state S2. Yeah, this is state S2, this is state S1.
Tomek, but if you would put one more red spot on your system,
Just do
then
2 red spots.
there would be
Starts
2
with
waves.
2
right?
different initial
Okay, so
blocks.
you think like this, right?
Yes.
Okay. Yeah, so you simply seal it. And that's all.
So they won't pass through each other.
Yeah, they cannot, yeah, if it is dissipation, I mean, for solitons you need non-dissipative system, right? And this is dissipative system, you dissipate energy, and
Whatever energy is.
I mean, if you have one equation only, here I have 2 equations. If kinase can be in 3 states, I have 2 equations. I would have 3, but one can be, the total sum is constant, so I have 2 equations. So when I have 2 equations, I cannot write potential. But in a simplest case for which we have analytical results, I can write the potential, whatever it means, simply.
Yes. Is it crucial that you have these 3 states?
Yeah,
K, KP, and KPP.
yeah, it is crucial for
Only had what, A and B. Would that be different?
okay. So, okay, so what I have here, it is like K, KP, and KPP. And these transition rates are linear functions of K, KP, and KPP. And this is a linear function of phosphatase. Yeah? If I take that I have 2 states, K and KP, and assume that this is a quadratic function of Kp, or that this is of Kp squared, this transition rate, and this is linear, I can have 2 states, right? And this is what we did for the analytic example.
Right.
But from the chemical point of view, it is nonsense like having, I mean, this can arise as a simplification, but it would mean that the transition is proportion, that if the kinase has 2 neighbors, it has a higher, like, nonlinear probability to change, which involves the reactions of 3 molecules simultaneously. So from the chemical point of view, it makes no sense. Yeah, but exactly we did such a model, assuming that, and this is one-dimensional model, because the sum of K plus Kp is constant. So assuming that this transition is proportional to Kp squared, we have bistability in a simpler system, and this was this analytical model we solve, right? So, but doing the Monte Carlo simulations with such assumption makes no sense.
Like having twins is a simplification to having 2 children, one after another.
Yeah.
So if you switch off diffusion, the whole thing would be a sort of like Conway's game of life, except a probabilistic extension of it. So then you might
All right.
expect traveling patterns, solitons,
If
configuration of hexagons.
if the system is if the system is dense enough,
Yeah.
yeah, because if the system is not dense enough, you will find the gaps and it will not propagate.
Yes. Okay. Yes.
Well, I think there was a question already asked, but if the constants are properly tuned, can you have transitions between the states back and forth?
Right. I mean, this is what.
Which means waves going in both directions.
Oh, waves going both directions. Okay, so I don't have this example on the slide, but I can take different parameters and have wave going back. Right. So just a second. So. Yeah, so here, so if I, all these traveling waves I show you were for parameters somewhere here, so, yeah, but if I take the parameter somewhere here, these waves will propagate from active to inactive state, yeah? If I take the parameters on that line, I will get the standing wave in a deterministic limit. I will get, so this is the standing wave criterion. So here they propagate from inactive to active state, so inactive state win. Here they propagate from active to inactive, so active state win.
And on the line, you can, in principle, have a Turing pattern of some sort, right?
For Turing,
but it wouldn't.
No, for Turing pattern, you need two different diffusion coefficients for
I
two
don't want to
different
call it Turing, but it'll be a
uniform pattern.
It'll be a pattern.
Yeah.
Let's not call it Turing. It's going to be a.
Cousin of Turing.
Not really. No, you cannot get it because then. No, you cannot get it because then the front curvature matter.
Mm-hmm.
Yeah. So if you if you have a standing flat wave, yeah, so this is the front, and you tune the condition that this wave is standing, and you make the front like this, it will shrink and collapse, because when you perfectly tune the, it means basically that the potential here that V1 is equals V2, that the stride wave stands. So when you make that the front has the curvature, the front will try to shrink. Because in front, you have to go from one steady state to the other steady state. So you pass from one steady state and it has a high energy, so the front likes to shrink.
Unless you make it that long channel.
Yeah, but you can get, maybe you can get such a pattern, strips. Yeah, not sure about it. But not with curved fronts.
Okay.
Need to propagate to lines.
Sorry for keeping you so long.
No, thank you very much.